Let us look at the chemical erosion in different places. One is the temperate and continental and Arctic regions. So the chemical erosion in the glaciated catchments are 1.2 to 2.6 times the continental average. In other words, they are higher in the Arctic region. The organic carbon oxidation and sulfide oxidation by dissolved oxygen coupled to carbonate dissolution and incongruent silicate dissolution are responsible for the seasonal changes in meltwater chemistry in the Arctic region. The efficacy of chemical weathering in glacial environment is due to high flushing rates, turbulent meltwaters, high suspended sediment concentration, and low buffering capacity of dilute meltwater. So these are all the various regions. The top one is the Arctic, followed by the blue color is the subarctic region. Then we have temperate and subtropical region, then tropical region, then in the center we have equatorial and sub-equatorial region. Similarly, at the southern side also we have the same thing, tropical, subtropical, temperate regions are there, then sub-Antarctic and Antarctic regions are there. So to explain the chemical erosion, a two-component model is being proposed especially for Arctic region. The glacial hydrology can be classified as superglacial, that is at the top, then N-glacial, that is inside, and subglacial, that is below the ice hydrology. But here we will mainly focus on the N-glacial and subglacial regions. So the bulk meltwaters are believed to be largely composed of two components. They are termed as the subglacial, or sometimes people call this as a delayed one, and N-glacial, which is called as the quick components. Both are derived from surface snow and ice melt. The delayed flow is also called as a concentrated one, which pertains to waters in slow transit through a distributed drainage system at the glacier, that is below snow-covered ice. In the case of quick flow, which is called as a diluted one, pertains to waters in rapid transport through the hydrological system, predominantly through ice-walled conduits and basal channels, that is snow-free ice near the snouts. So these are all the two different types of meltwaters. So what are the types of the reactions occurring in this one? The T model, where the subglacial solute acquisition proceeds by acid hydrolysis reactions fueled by protons from either the dissolution of atmospheric carbon dioxide or the oxidation of sulfide mineral by dissolved oxygen. It is believed that carbonation reactions are dominant in the channelized system, and the sulfide oxidation and carbonate dissolution are important chemical weathering reactions in the distributed system. So we have the two different systems. One is the channelized one and another one is the distributed system. So what is the misconception generally people have about the subglacial chemical erosions? The first one is chemical erosion is least intense in glacial environment because low temperature inhibit chemical weathering process. This is not the case. There is an underestimation of importance of acid snow melt, the role of moisture availability, the fresh ground character of the rock floor, and geochemically reactive trace minerals contribute quite a bit. The seasonality of runoff in glaciated catchment is sometimes neglected, but the rate of dissolution is inversely related to time-dependent solute concentration, and which results in the meltwater flushing rate also. So what is the relationship between the water chemistry and subglacial drainage systems? The part of the water leaving the glacier by way of superglacial channels. The rest is intercepted by moulins and crevasses into N-glacial and then to subglacial conduits. That means the water goes through all the three regions, supraglacial channel, N-glacial and the subglacial conduits. So the water has unique chemical signature, that means isotopic composition depending on the source, whether it is the snow or ice melt or the reservoir through which the water has flown. So these are all the different composition leads to. We can later study what is the origin or source of this particular water. Based on dye tracing and borehole studies of runoff chemistry, we can get information about the main characteristics of the subglacial drainage system. In the next module, we will study more about how the dye tracing actually works. So let us look at the influence of glacier hydrochemistry by supraglacial debris. So the greater supraglacial water rock contact on the lower glacier increases the SSC and the bicarbonate concentration of supraglacial lakes and streams. The supraglacial debris only influence sulfate concentration and the residence times are long, that is mainly in the case of small ponds. Because the debris cover inhibits the formation of channelized network beneath thick debris covered areas, it indirectly increases the proglacial bicarbonate and sulfate concentration by increasing the proportion of water which is routed through an inefficient subglacial systems. So what are the limitations of this two-component model? This model does not consider distributed melting patterns of glaciers or refrozen mixtures of components, so they are not included. When there is a mix of components that lead to different ions being formed, that is also ignored. The seasonal variations cause changes in the chemical composition of bulk meltwater, so this is also not considered. So these are all the limitations of the two-component model. So what are the limitations of mixing models for glacial hydrochemistry? They fail to consider the complexity of flow patterns, the ion exchange kinetics at the water-solid interface, buffering of pH, non-conservatism of solutes, post-mixing particle-particle reaction, that is carbonation reaction owing to englacial supply of dissolved bicarbonate. All these things are not considered.